Hello, my name is Sean Boyle and I work here at SIU Automotive Technology, and today we're going to look at these inexpensive pressure transducers to see if they do a decent enough job at doing in-cylinder pressure testing. This first one we're going to look at is this Amazon/eBay special, and you can see this thing here, it's about 20 bucks. It's not that expensive. If you search pressure transducer in eBay or Amazon, you're going to find a variety of these things. You're going to see a lot of times they'll be accompanied with a picture like this, and they'll show that they can come in variations from 30, 100, 150, all the way up to 500 psi. I've even seen them that show 1,000 psi or 5,000 psi. And their voltage output is typically between 0.5 volt and 4.5 volts. So you need a power supply, a 5-volt power supply for these. And this one here is gauge pressure. We're going to see what the difference between gauge and absolute pressure is here in a moment. But one of the things down here, you can see the response time is less than or equal to 1 millisecond. Now, I don't know if their response time is the same as the output interval of the information that this sensor provides. The speed of these sensors and how frequent they output the information is very important. You're going to see the quality, the high dollar sensors, they output their information about 1/10 of a millisecond or 100 microseconds per output division. And you want that if you're doing in-cylinder pressure testing, because that will allow for a smooth pattern that's going to give you an indication of what's going on in that cylinder. If it doesn't output the signal frequent enough, you'll see these little stair steps, these little stepping blocks, and the information will be less valuable then. The next two sensors are the Honeywell sensors, and I got a 300 psi and a 500 psi sensor. These are both absolute sensors, and like I said, we'll see what that means here in a second. They have this listed as this response time is less than 2 milliseconds. Once again, if the response time and interval time is pretty much the same spec, this would actually not be a very good scope. This would be about 20 times slower than the high dollar ones. But we're going to go ahead and put these to the test to see how frequent and how fast they can output their information. I got these two sensors from DigiKey. They keep them in stock. These are the prices that I paid. You might be able to get these a little cheaper if you search around, but DigiKey, the reason why I use them is because they're very fast. Seems like we can get them in a day or two, and they always seem to have this stuff in stock. Another sensor we're going to look at is a little more expensive. It's $124 from DigiKey, and this is an SSI Technologies 500 psi sensor, absolute. So just like the Honeywell, this is an absolute sensor, and we'll discuss that here in a second. Its response time is listed at 1 millisecond. And hopefully that it'll be a little quicker than that, because once again, we want these intervals to be closer to 100 microseconds or 1/10 of a millisecond. You can see it also, just like all these sensors that I have here, their rated output is between 0.5 volts and 4.5 volts. And they don't draw much current. You can see this one's less than 6 milliamps. So you don't need much of a power supply to power these things up. This one here actually came with a little 3-foot whip of a wire. And with most of these sensors, I've attached just some banana leads to the end to fit into a kind of a homemade little 5-volt power supply box. So I'll talk about here in a second once we get on the vehicle. So what we're going to compare all these sensors to is the output from the Fluke PV350. This is an older style Fluke PV350. This is the type. It works very well. It does a great job. I've got to warn you right now that if you go out and buy a Fluke PV350 and it's a newer model, it will not work for what we do. It does not have the output speed, and you're not going to get the quality signal. If you can find old stock, these things work great. They are still pretty pricey. They're about $400. I don't know how much a used one would cost. I've been using these for about 15 years, and they've never really let me down. And this is how you can tell if you've got a newer model or not. See this little blue box right there that separates between the red and the black leads? You want to make sure yours has that blue box. If it does not have that blue box, that's a newer design PV350, and it will not work for automotive use for the in-cylinder pressure transducer testing that we do. So definitely make sure that you've got that box. If you don't, it's not going to be any use to us. The reason why this Fluke PV350, these older ones, are so nice is because they're really designed to work with multimeters. They just slide and plug right into the leads. You got your power and your ground spaced out perfectly, so they just stick right into your multimeter. And they've designed the circuitry that we have in this box, and with the zeroing function that we have on this dial right here, it basically comes out to be that 1 millivolt equals 1 psi. So if I stick this in there and I'm measuring, say, static pressure like line pressure on a transmission, and I see 125 millivolts, I know I got 125 psi. What makes that better is that these little transducers here that you can buy, is that if you remember, 0.5 volts is kind of where it starts at, and it goes up from there. So like this 500 PSI transducer is going to be at 0.5 volts is going to be 0, and then at 4.5 volts it's going to be 500. So it's not a one-to-one relationship. So if you were to use this with the DVOM, it would be very difficult to translate the voltage that you're reading to a pressure because it's not a one-to-one relationship. So that's why this Fluke PV350 is nice. It measures on the positive side. Positive voltage would be positive pressure, and it actually will display a negative voltage for negative pressure. So like when we see this on the vehicle, we're going to, even though we're going to set up a custom range, we'll say negative 15 millivolts is negative 15 PSI, 0 is 0, and then 500 is 500 PSI, millivolts. 500 millivolts is 500 PSI. So that's this Fluke PV350. This is really what we're going to compare everything to. So let's take a look at this gauge versus absolute pressure, or these pressure transducers that are going to be listed as gauge or absolute. What does that actually mean? Well, here's an image of the Earth, and we've got the US of A right there, and you can see this is an example of 1 square inch and gravitational force pushing all the way down onto the surface of the Earth there. Right here is New Orleans, and that's basically what they consider sea level, actually a little bit below sea level, but we'll ignore that. And you can see this as 1 ATM of pressure at the surface. That's atmospheres, or bar. Bar is another term for like 1 bar and 1 atmosphere is basically the same thing as 14.7 PSI for those of us that think in pounds per square inch, you know, in our little corner of the world here, about the only ones left, I think. It's also 30 inches of mercury, 30 inches Hg. And like I said before, 1 bar or atmosphere. That's at sea level. That's absolute pressure. So if you had an absolute gauge and you were in New Orleans, it would read 14.7. That's how much a weight of the atmosphere is working on your shoulders right then and there. It would read 1 bar or 1 atmosphere or 30 inches of mercury. Now when we go higher in altitude, we get closer to space and there's no pressure up in space, you'd float away just like you see in the movies. Here in Denver, as an example, Mile High City, 5,280 feet above sea level, we would have about 12.2 PSI gauge. And that's about 25 inches of mercury. You have less air pressure. Now, that's the absolute pressure. Once again, if you had an absolute pressure gauge, you would read 12.2 PSI on it, or 25 inches of mercury on it. But then when we think of Mount Everest, we're going up even higher. Those crazy people that climb up to the top of Mount Everest, 30,000 feet above sea level, you get about 4.4 PSI of atmosphere working on you. That's not much. And that equates to only about 8.9 inches of mercury. And really, until you get to about 100,000 feet above the surface of the Earth, then you pretty much don't have any pressure. I mean, it's negligible, it's small amounts, but we basically say at 100,000 feet above the surface of the Earth, there's no atmospheric pressure working on you. So how does this come into play when we're looking at absolute versus gauge transducers, or really pressure gauges or anything like that? Is gauge sensors are going to be zeroed out for wherever you're at. So whether you are on 100,000, of course it'd be 0 there anyway, but if you were at Everest, your gauge would read 0. If you're reading Denver, if you're reading the gauge in Denver, it would read 0. And if you're reading the gauge at sea level, it would read 0. So it's always kind of calibrated or zeroed out to wherever you're at. Anything that is gauge pressure, like if you see PSI-G, that means gauge, that means 0 is taking away whatever atmospheric pressure is working on you, and you're starting from there. Whereas like a MAP sensor, a manifold absolute pressure sensor, it wants to know the actual atmospheric pressure working on it, so it will actually display what it is right then and there, and it's not going to be zeroed out for where you're at. So, for example, as I've mentioned before, an absolute sensor at sea level would point out 14.7 PSI right there on the gauge or on the display. So does it really make a difference whether you've got a gauge or an absolute sensor? It does make a difference basically on how we set up our scope. We're going to set up these custom probes, these custom settings within the scope, so that way it learns what voltage is equal to what pressure. And if I don't do that, once again, kind of like using one of these sensors from Honeywell or SSI with the DVOM, it would be hard to correlate the millivolts to the pressure. So I want to go through and set up these custom ranges within a scope so that way I know exactly what pressures I'm dealing with. And with an absolute sensor, it's going to be a little different because an absolute sensor is measuring the actual pressure. You know, it's not zeroing it out for where you're at. So like 0 PSI would be out in space, or if I'm pulling 30 inches of vacuum. And at sea level, I'd be getting 14.7. So my voltage range, which is 0.5 volts to 4.5 volts, or 500 millivolts to 4,500 millivolts, at 500 millivolts, or half of a volt, that's equivalent to 0 PSI, absolute, like as if I was in space, or if I'm pulling 30 inches of vacuum. And then at sea level, at atmospheric pressure, it's about 667 or 668 or so PSI. And you can see that's equivalent to 14.7. And then at the highest pressure, I'm going to see 4,500 millivolts, and that's going to be 500 PSI, absolute. And you're going to see, now this right here, this column here is telling you how you would set up your custom range. Now in reality, some of the scopes have a little different ways of setting up these custom ranges. I'm using Pico as the example right here. You really only need to set 2. You can say at a half of a volt is the same thing as negative 15 PSI, which is basically, you know, taking the atmospheric pressure out. And then the maximum pressure, which is 500 PSI, 500, by the time you say minus 15 plus 500, you get 485 PSI, because that's the range, 0 to 500 PSI, is at 4,500 millivolts. Hopefully that didn't confuse you too much. Basically, this is a 500 PSI sensors that I'm looking at here, and negative 15 plus 500 PSI would be 485. So at a half of a volt, I'm getting negative 15 PSI, and at 4.5 volts or 4,500 millivolts, I'm getting 485 PSI. Clear as mud, right? Now this gauge sensor is going to be set up a little bit different. If you remember, gauge doesn't take into consideration the atmospheric pressure that we have. Basically, wherever you're at is 0. So at that half of a volt to 4.5 volt range that it's going to be operating at is going to be between 0 and 500 PSI. That doesn't mean that you can't measure vacuum or negative pressure. It'll just pull that voltage below 500 millivolts. So like in this example, and we'll see this out on the vehicle, if I take my gauge sensor that's operating between 0.5 volts and 4.5 volts, and I pull a vacuum on it, it'll pull it down to about 375 millivolts. And I would say, okay, well that's equivalent to negative 15 PSI. So in this case, with the gauge sensor, I'd probably say, set up my custom probe and say 375 millivolts equals negative 15 PSI, 500 millivolts equals 0, and then 450 millivolts equals 500. Because it is a 0 to 500 PSI gauge, we're kind of just pulling it down outside of its limits by going negative with it. So here we are at the truck, and as I mentioned, I've got a Pico Scope hooked up to it, and my 3 channels that I have hooked up here, in blue, you're going to see the pressure transducer, and in this case, we're going to start with this Fluke PV350. And in red, where we've got the secondary ignition, I've got a clip around the secondary ignition lead down there. That's for the same cylinder that I disabled with my pressure transducer. And then in green, I've got a little homemade pulse sensor, and you can see a video on that if you're interested in making one of those. They're pretty cheap. I also have a snap-on scan tool, and we'll see what the timing is displayed during this, these tests, so that way we can see how close the timing occurs on the pressure waveform compared to what the computer is commanding. Now the first thing that we have to do with these is that we have to set up a custom probe. And we don't really have to do it with this Fluke so much because, as I mentioned before, it is a 1 millivolt to 1 PSI relationship. So if we just left it in millivolts, we'd be pretty good. It's, you know, if we saw 20 millivolts, we knew there was 20 PSI. But I'll go ahead and set up a custom range anyway for it. When we set up these custom ranges, we're going to want to go up to the Tools menu and go to Custom Probes. And we'll say New Probe. And I'm using Pico 6 for this, so that way if you're using a non-automotive scope, you can do that. Use the custom unit defined below, and we're going to say pressure. And we'll abbreviate that PSI, as you can expect. Then we could use this linear equation, or we can use this lookup table, and this lookup table works pretty good. So I'm going to say millivolts, and the output's going to be pressure. So I would say negative 15 millivolts is equal to negative 15 PSI, and 0 is 0. I don't really know if I have to do that, but I'll do it anyway. And then 500 millivolts is equal to 500 psi. Then hit OK. Next. I like to select the advanced to set up ranges. Then I'll tell it to auto-generate the ranges. And these are all pretty good. If I didn't want one of those, I could delete it, or I can create a new range, but it's pretty simple. So I'll just go ahead and say next. If I wanted to put filtering on, I could, but I'm not going to. I'll do that at the end if I have to. Then the name for the probe, I'll just say PV350. Finish, and it shows up in my library right there. So now if I hit OK, go to my channel A, under probes, under library, you can see PV350. And I can set whatever range I want. I'll go ahead and set the -15 to 200 psi range. So now I'll go ahead and start this up and we'll see how well it does. Let's take a closer look at that PV350 waveform. You can see I've got my 10 screens captured here. That's where the snap throttle occurred, and that's when it was idling, and that was my cranking pressure right here, my cranking compression. If you remember, in green I had my pulse sensor hooked up. That's that homemade pulse sensor. And in red I've got my ignition, and then in blue is my PV350 pressure waveform. One of the things that we're going to do with each of these is I'm going to zoom in real tight on a compression waveform here where the pressures are changing and see if we can't tell how frequently the interval of the sensor reporting is, how quickly the sensor can report and how often it reports. Right here it's kind of messy, a little bit noisy, so we're going to add some filtering to it and maybe see if we can't figure out how frequently this is outputting a voltage to the scope. And this is probably pretty good, so I'm going to zoom in real close on it. I'll take my vertical rulers and I'll say, okay, there's a measurement and here's a measurement. And you can see it's about 150 microseconds. So that's actually pretty quick. That's the reason why we get a decently smooth pattern. You know, this signal looks pretty good. If I skip over to when this thing was running, matter of fact, I'll zoom in just before I snap throttle. And I'm going to double the size of this because it's a little small when it was just idling. So now if you take a look at it, we've got about 61 psi of running compression. Our exhaust is about 1/3 of a psi, which is probably just a little out of calibration there. And my intake is about 10 psi difference between exhaust and intake. So that's about 20 inches of vacuum. If I wanted to check my events, my valve events, I can take my degree rulers here. Pico 6 defaults at the 360 degrees, so I'd want to change that to 720. And add rulers if I wish. There's 4 rulers, so now within this pattern here we get to see this is the power, this is the exhaust, this is intake, and then this is compression. Assuming, you know, top dead center, bottom dead center. Really, you could say this is top dead center, this is bottom, that's top dead center, bottom dead center, top dead center. But our 4-stroke cycle is being shown right there. Does a pretty good job, a nice clean signal. So yeah, if I zoom in on this maybe even a little further, you can see it's a pretty good quality pattern. Now one of the things I like to do also is I like to see how when this spark occurred in relationship to this pressure waveform. So we're going to take one of our time rulers here. I'm going to put it right over the top of my ignition. So there's my firing line right there. That's when the spark was initially started. And put this right over there at the peak of the pressure waveform, and you can see I'm about 15 degrees. Now if you remember from the scan tool images that we were getting at about, it was pretty much averaging between 8, 9, maybe 10 degrees of advance. So it looks like it's about 5 degrees delayed. And so in reality, the spark, according to the pressure waveform, probably would have occurred right around this area. So the delay that we're looking at is between when it's reported on the scope and when it probably should have happened. If you look, that's 1.25 milliseconds, or roughly a millisecond. So there's probably a millisecond of a delay between when it actually sees the pressure before it reports it out to the scope. That's actually not too bad. When we saw those specs and they said response time 1 millisecond or less than a millisecond, I'm sure that's what it was referring to, not the frequency of the voltage output that it's delivering. Because we could see the voltage output that it's delivering, it's occurring more frequent than that, much more frequent than that. All right, so that's the PV350. That's pretty much what we're going to compare everything to. It is a good sensor. We've been using that here at the university for, like I said, probably 15 years, and it really hasn't let us down. And no, I don't have a Pico WPS or an ATS or anything like that, mainly because these do seem to do a decent job, and but they're still not that cheap. They're still pretty expensive. So the idea is to see if we can find a less expensive sensor that'll report a pattern or a pressure waveform, in-cylinder waveform, similar to this one right here. That's the goal. So this next sensor is the Amazon special, eBay special, $20 500 PSI transducer. So with these other transducers, I have to create my own little power supply. So I made this little box. It's nothing fancy. It's basically got a 9-volt battery and a 5-volt regulator and some banana plug jacks. I got a little stud there that I can stick my ground clamp onto, or a lead to, and I can just wire these up. I've made it so I can put 4 of them up there if I wanted to. The first version of this I had actually hooked up to battery voltage. I just said, why have a 9-volt battery? We got a 12-volt battery. But I found out that when doing cranking tests, when the battery voltage drops low, especially if it drops too low, it's going to actually skew the sensor down. And I had a vehicle that we were diagnosing a camshaft issue, and we found it was reading negative, like the exhaust was reading in a vacuum, which it really wasn't. So that kind of threw me off. And then I discovered, oh, okay, it was the battery voltage. So I went back to just basically putting a 9-volt battery in there, and I've got my sensor plugged into it. I got my just typical air coupler attached to it. This is what fits most compression gauges. And actually a lot of these I've made steel gauges. I've broken out some ceramic out of the spark plugs, welded a pipe to it, and then welded my fitting to it. But I'll be honest, I pretty much just use the rubber compression hoses probably more often than I use these steel ones. So once I plug this thing in and I look at my output, you're going to see that since it's a gauge sensor and it kind of disregards atmospheric pressure, that we're going to be set at about 497, or a half of a volt, about 500 millivolts. And that's the output. I've got my scope set up to 5 millivolts per division, so it's going by really quick, and I'm doing a measurement on channel A, and that's showing pretty close to a half of a volt, or 497 millivolts. So I've got my vacuum pump here I got an old AC vacuum pump that I use for testing valve bodies. I'm going to go ahead and pull 30 inches of vacuum, or probably 28 inches of vacuum or so. It's not that strong of a pump anymore. But we'll go ahead and pull a vacuum on this and see how low it will go. That'll give us an idea of what negative 15 or so PSI will get us. So you can see this is pulling down to about 380 millivolts. So now I'm going to set my custom probe up knowing that information. I will go to my tools, custom probes, new probe, and just like the PV350, the unit will be pressure, PSI. I'll use a lookup table. And millivolts, I will say 380 millivolts is equal to negative 15. And 500 millivolts is equal to 0 psi. And 4500 millivolts is going to be equal to 500 psi. Next, I'll pick advanced. Auto-generate the ranges. Probably won't need this one, so I'll just delete that. In fact, I don't think I'll need just a vacuum either. and I'll call this eBay. So now I'm going to go ahead and set my channel up to the eBay transducer. And it's already set that smaller range up, which is good. I'll increase my time base to 500 milliseconds per division. With this eBay sensor, we're going to go through and take a look at the pattern that we captured here. And that's when it was idling, that was the snap throttle, and that was the cranking. So with all these, like I said before, we're zooming in on this pattern to get an idea of the sample interval. You can already see this one here has quite a bit of stair stepping. If I put my time stamps here, time rulers, it looks like it outputs the signal. In this example here, it was 1.78, 1 3/4 milliseconds. So you can see it's pretty slow. It's at least 10 to maybe 12 times slower than the PV350. It's not going to be that good for us, but to do a thorough job, let's check it with everything else as well. So here I've got it before the snap throttle. I'm going to go ahead and make this a little bit bigger so we can maybe get some better measurements. I'm going to add some filtering to it to clean up some of that noise. And I'll use my timestamps, or I'll use my degree rulers here so we can figure out when this ignition event happened. Change that to 720 degrees of rotation. And let me zoom in a little closer on this guy. So you can see this is, well, it says it's 17 degrees. We know that that's not the case, that it's more likely the ignition event was happening right around 9 degrees or so. And if we want to see how delayed this was, I could put my other time ruler up there. It's showing about 1.88 milliseconds. So 1 3/4 milliseconds, about as often as it reports the information, is what it was delayed at. So the response time is less than 2 milliseconds. It's not very good. Ideally, we would have something closer to 1 millisecond. As far as pressures are concerned, you can see it's not doing too bad. It's about 66 psi of compression. Looks like the exhaust is about, it's pretty close. It says a negative half of a psi, so we know that's not exactly right. And then my intake pressure is, the delta is showing at about 19 inches of vacuum, which is pretty accurate. So even though it's blocky, the measurements seem to be pretty accurate. So that's a good thing about it for 20 bucks, you know. But I don't think I'd use it for in-cylinder pressure testing because of its poor sample intervals that it displays. There's a good chance that we'll have better options with some of these other sensors. So now I'm going to go through and set up my 2 Honeywell sensors. Unlike the eBay sensor, this is an absolute sensor. So when I plug this in, I won't expect to see a half of a volt. I'll see something higher than a half of a volt because it's going to be measuring the actual atmospheric pressure. So you can see here I'm getting about 668 millivolts because it's measuring that 14.7 psi of pressure that we have here close to sea level. If I pull a vacuum on it, I would expect it to go down to about half of a volt. It actually pulls down a little lower than a half of a volt. It goes down to 487 millivolts. When we set up this custom probe, we will actually use those voltage values to kind of help us. So once again, pressure, PSI. Now we're going to create our lookup table. We're going to use millivolts. And we got, what was that, 485 millivolts. Was, we'll call it negative 15 psi. I'm not certain if that vacuum pump can pull a true 30 inches of vacuum or not. And then at 678, which we can see at the bottom of the screen, that is at our atmospheric pressure converted to gauge, basically, so that way we can use 0 as where we're starting. and then our 4500 millivolts is going to be equal to 285 psi. And the reason why we do that is the difference between negative 15 psi and 285 is 300 psi, and that is what this gauge is, a 0 to 300 psi absolute sensor transducer. Get rid of those, probably get rid of all of them. Then we'll say Honeywell, I'll call it a Honey 300. Pick that as my probe. And now we are ready to test this. Now let's look at the Honeywell sensor, and this is the 300 psi sensor. You can see that's while it was running. There's our snap throttle, and there's cranking. So if I zoom in on my cranking pattern to see what kind of intervals we've got, you can see it looks like a pretty smooth pattern right off the bat. I'm going to keep zooming in, and there you can actually see the blocks, the stair steps. And if I go pretty much from to measure each one of these little divisions, you could see it's about, this says 395 microseconds. If I put some filtering on, let's see if that cleans it up a little bit. So it's much faster than the eBay sensor, but at least twice as slow as the Fluke PV350, maybe even a little bit slower than that. But if you take a look, we'll go to the running compression. There's a snap throttle. Pick a few before that, and I'll go ahead and zoom in 2 times. Make that pattern a little bit bigger. It's actually not a bad looking pattern. It is pretty smooth in my eyes. I think it's acceptable. There's some blockiness, a little bit of stair stepping, but nothing like the eBay sensor. I look at my pressures. I've got 67 psi compression, and my intake pressure is, it's like negative 10 psi. I'm running at pretty much 0 for my exhaust. There's a tenth of a psi. So far all of these sensors have done a good job measuring intake vacuum. If I go to put my degree rulers up there and change this to 720, then I'll go through and we'll see how this timing event occurred. Shows it at about 18 degrees, maybe 17 or 18 degrees. And if I were to bring that to the point where the ignition was typically happen around, say, 9.5 on average, and if I overlap it, it is 1.8, let's say 1.5 milliseconds of a delay that occurred. I don't know if that's really excessive or not. That's probably not too bad, really. And so for this sensor right here, this 300 psi sensor, for its cost, it's actually not too bad. I think it's a decent quality. We don't have that much stair stepping. I think the report rate is probably decent for most of the stuff that we're going to measure. I don't think it would miss anything. It's not as good as the Fluke, but it's pretty good. So that was the Honeywell 300 psi transducer. This one is a Honeywell 500 psi transducer. They are the same series, the PX2s. Why would you want a 500 versus a 300? Well, if you don't see yourself going over 300 psi, you might be better off using a 300 psi gauge because the resolutions can be better. You're still spanning 4 volts, between half a volt and 4.5 volts, but you're measuring only 300 psi, whereas on this one, I'll be across those 4 volts measuring 500 psi, so my accuracy might be a little bit off on this. But if you ever see yourself going over 300 psi, you're going to need something bigger. You can get the 500. We'll do the same sequence of tests for this 500 psi transducer. So at atmospheric pressure here, we've got 625 millivolts because this is an absolute sensor. I pull 15 pounds of vacuum on it. That goes down to, looks like around 508 millivolts. So 508, and if we put 500, it'd probably still be pretty close. So, you know, half of a volt was equal to negative 15 psi. And then 625 millivolts was our atmospheric pressure gauge, you know, zeroed out for where we're at. And then 4,500 millivolts is going to be, since it's a 500 psi transducer, that'll be equal to 300 or 485. So the difference between negative 15 and 485 is 500 psi. Honey 500. Welcome to the Honey 500. And there we are. We've got that. I'm going to go ahead and put that probe up there. Honey 500. So here we got the Honeywell 500, and I'm scrolling back through my screens. You can see that's when I was idling. That's my snap throttle, and there's my cranking compression. Really, it shouldn't be that much different from the previous one we just checked because it's the same series sensor. If I zoom way in, you can see I can start seeing some of those stair steps, turn on some filtering. Yeah, it looks like about 400 microseconds. So as I mentioned, it is about twice as slow as the PV350, but it still does produce a decent waveform. And if I zoom or go to my, just before my snap throttle, so we can evaluate the running compression, I'm going to zoom in 3 times. And this is really a feature of my scaling. Pressure-wise, 64, 65-ish up at the top. My exhaust pressure is 1/4 of a psi, and my intake pressure is negative 10 psi. So once again, just like these other sensors, it's doing a very good job of measuring my intake vacuum and my exhaust pressure. And now it's time to check to see how well it does the compression curve and the ignition. So it's showing at about 15.6 degrees, and if I bring it to the 8 or 9 that it's supposed to be, that was likely operating at, and you could see that it was about 1.4 milliseconds. So this this series of sensor, it has about 1.5 milliseconds of a delay, whether you're using the 300 or the 500 psi, and it looks like it spits out the information at about every 400 microseconds, or maybe 0.4 of a millisecond. A little bit slower than the PV350, but it's not horrible. I think it is something that's still beneficial, usable. It's less than $100, so it's actually not a bad sensor to get into. The last sensor we're going to check is this SSI Technologies sensor. It's a 500 psi transducer, absolute, just like the Honeywell 500. And you can see the values are probably going to be pretty similar, but we're going to go ahead and set a custom probe up for it anyway. Looks like we're about 612 millivolts where we're at, 400 feet above sea level. That drops down to about 494 millivolts. Then this is pretty much what you'd expect. With these absolute sensors, at 0.5 volts, that is 0 psi absolute, as in negative 15 psi gauge. And at 4.5 volts, that would be the full 500 psi absolute. which gauge would be 485 psi. This time, for the sake of experiment, I'm going to make it even the custom probe a little simpler. I'll say new probe, and pressure. My lookup table, I'm just going to create 2 rows. I'm going to say well, this is like, we'll say 490 millivolts is negative 15 psi, and we'll say 4500 is 485 psi. Delete ranges I don't think I'll need. Call it SSI, finish it. Select my probe. Even though I didn't put in that 612 millivolts for atmospheric pressure that I'm feeling right here, I just went from the negative 15 to 485. It's showing 200 and this is milli psi, so it's showing about 1/3 of a psi of air pressure. That's pretty accurate for what we're going to do, so we should be fine. We're going to go ahead and do the same test that we've done on the others with this SSI sensor. This is the SSI Technologies sensor, and I'm going to scroll through this. You can see that's where it was running, snap throttle, and this is our cranking compression right here. I'm going to zoom way in on this. You can already see it's a very smooth line, so we know that this thing is outputting at a higher frequency than these others. So I'm going to see if I can't figure out the interval. This is like pretty tough to do because it looks like they're pretty tight together. So I'm going to guess probably around 150 microseconds, maybe even less. So this is about the same speed, if not maybe even a little faster than the Fluke PV350. This is that $125 sensor, SSI Technologies. Okay, so I'm going to go ahead and find just before the snap throttle like I've been doing for all these others. And we'll grab a little capture of that. I'm going to zoom in on this probably 3 times, I think, to kind of make the pattern a little bit bigger. That's pretty good. Actually, I could probably go another time. Probably should have scaled this a little differently. Negative 15 to 485. It's probably a little too wide of a range. Pressure-wise, I'm looking at 64 psi compression, running compression. My scaling might have been a little off on this. If you remember, this is the one where I only put negative 15 is equal to 1/2 of a volt, and 485 was equal to 4,500 millivolts. I didn't do the 0, and that kind of showed up here because I'm about this exhaust pressure, which should be 0, is showing at 3/4 of a psi, so it's a little bit higher than it should be. And then my intake pressure here, it's showing negative 9 psi. Or 9.692 psi delta between the exhaust and the intake, which is almost 20 inches of vacuum. So it's still reporting pretty much like the others were. Put my degree rulers up here. 720. So now I got my degree rulers up there. I'm going to zoom in on an ignition event and see how quickly this reported this information. You could see it's about 12 degrees, so it's actually a little closer than the others. If this occurred where we're estimating around 9 degrees before top dead center, and we want to figure out how much of a delay there was, this is showing about 2/3 of a millisecond, or 687 microseconds. So this SSI sensor here is by far the best contender, especially if we're comparing it to the PV350. It's a nice smooth signal. It's outputting its information very frequent, at like 150 microseconds. And you could see, in my opinion, that you'd be able to do pretty much any of these in-cylinder diagnostics that we typically do in the automotive industry. So at $125, it's a little more expensive than the other sensors, but I think it's more capable and probably worth spending a little bit of extra money to get the accuracy and the high speed of the SSI Technologies sensor. So what are the results? How did these all fare out? Well, that old Fluke PV350 is pretty hard to beat. If you can get your hands on one of those, it's a great tool. A close second would be the SSI Technology sensor. It is very fast as well, and it has a very good signal. The Honeywell 500 and 300, they might be a little bit slower, but they still produce a nice clean signal. The eBay transducer, probably not worth even the $20. Now, if you were to use that sensor, maybe for just checking things like transmission pressures or just pressures that you don't need super quick refresh rate, it probably will do fine. So it's hard to beat $20, but at the same time, if you're getting into this to do in-cylinder pressure testing, you'd want to stay away from those cheap eBay/Amazon sensors and invest in something like the Honeywell or the SSI Technologies, or find an old Fluke PV350. So hopefully this video helped you learn how to set up your scope properly and understand what the standalone pressure transducers can do for in-cylinder pressure testing. Thanks for watching.